As we finish up our week 1 with this part 3 in our series of our week 1 lecture videos, we can look at how we deal with fractions and adding and subtracting. While this is not a question that would be on test, it's definitely worth looking at how you would take a number like 40.625 and subtract off 1.25. How you would need to do that is find 1.25 in a positive 2's complement, and then you would flip the bits and add 1 to make this 1.25 negative, and then you would just add as normal. And seeing as you have a 0 out front, that would mean your answer is positive, and you could go through the normal procedure of counting that I have a 32 and I have a 4 and a 2 and a 1. That would add up to 39. And here we have a 0.125 and a 0.25 and then a 0.125, which add 0.375. All right, so let's add in 2's complement, and we're just going to do normal addition and see how this works. First up, 0 and 0, a 0, got another 0, 0, 1, 1. Oh, this is going to be a 1, 0, so I place the 0, carry the 1. Now I have 1 and 1 and 1. That means drop the 1, place 1. 1 and 1 are 1, 0. But this is an 8-bit, so what happens is that's the carry bit. He just gets X'd out. We don't have a wire for him anyway. And I wonder, is this right? Because it seems crazy. So let's see what this number represents. If I notice in this particular location, this is location 6, I have a 64, I have a 32, I then have an 8. I add those together, so this number is 104 in base 10. This guy right here, oh, he's negative, so I'm going to have to figure out what he is as base 2 and 2's complement. So that means I'm going to flip the bits, add 1. So this is a 16, but I know that it's negative because there was a 1 out front. So that's why I said, oh, this represents negative 16. Then I want to see, is the answer even right? Because I'm not really sure. So I add these up and I get 88. Well, let's look over here. I have a 64-bit, I have a 16 and an 8, and that also adds up to 88. Phew, this works. As crazy as it seems, it works. Let's add here. Try it again. 0, carry the 1. That's a 1, 1. There's 1. Ooh, that's 0, carry the 1. 1, 1, 1 is 1, carry the 1. 1, 1, 1 is 1, carry the 1. Whew. That's going to be 1, 1, but that's more than 8 bits. So, of course, I need to X out that carry bit. I'd like to double check this as well. So let's see. 2's complement this sucker because he has a 1 out front. Flip the bits, add 1. This happens to be a 10, so I'll make that a negative 10. Play the same game with this guy. Flip the bits, add 1. Oh, this is a 9, so that would be a negative 9. So I really hope when I add these two and I get negative 19 that that's what this is. Well, I don't know. It's got a 1 out front. It's got to be negative. Oh, well, that's good. And I'll figure out what this is. And hopefully it will also be 19. So I will flip the bits, add 1. This is what I get. I've got a 16, a 2, and a 1. And yeah, that's negative 19. This works. Subtraction, you can do subtraction. And this demonstrates how to do subtraction, but it's just easy to add a negative. Then we don't have to learn anything else. So you can look at this and You can, you can figure out how to do it this way, but I'm going to stay consistent with just adding a negative. All right. So let's look at some things that can be confusing because we have to know how many bits we have. If it's 4 bits, 4 looks like 0, 1, 0, 0. If it's 4 bits, -4, we would flip the bits and then add 1. However, over here, this is still -4. However, this is not. You can't just add zeros on the negative because the 1 is what we're going to have to flip bits. So instead of adding zeros out front, if it's negative, you can just add 1s, and that will represent the fact that it's negative. So do be careful about that. Overflows. If you have 2 numbers and you don't have enough bits, because remember the first bit's always going to be the sign, I can't represent this -15 with the number of bits. So if I was to add 8 and 9 with a signed bit, I would have to have 1 more bit in order to make a -15. That's just something to look out for. Ands, ors, and nots work the same as they do in your 126 class. They work the same as in a logic class in a truth table with trues and false. If it's and, both of them have to be a 1 in order to get a 1 result. It can't be either or. Both of them have to be a 1 in order to get a 1. For ors, either one of them can be a 1 and you'll get a 1. However, neither one of these is a 1, so that answer is a 0. But note that these are all 1s. Nots, you just flip the bits, which we've been flipping the bits prior, so we're good there. Here's some examples of anding bits. Just follow those rules. 1 and a 1 makes a 1. I only have 1, so it's a 0. 1 and 1, that's 1. On all the rest of these, I don't have 2 1s, so here would be my answer for the and. For the or, if at least one of them is a 1, it's going to be 1, so I can just go down through here and note that those are all 1s. Neither one of those is 1, so it's a 0. And both of these two, of course, would be 1. Nots, you just flip the bits. Exclusive or means that we need to have only one of them to be a 1 in order to get our 1. So 1 and a 1 makes a 0 because I only wanted one of them to be a 1. So that's your exclusive or. Morgan's laws, those are super important, especially in 126. They're also important to us because this is how we are going to create some of our logic gates in chapter 3. So we'll just briefly go through what's going on here. I have these 2 values that I would like to OR, and what I'm going to show is that it is equivalent to an and a not in a certain series. So instead of using an OR, I could take an initial value, not the second one, and then AND it, which is what I've done up top here. Take the first value, not the second, and then AND them. Take that answer and not it, and I will get the same answer as if I used an OR and I didn't have to use an OR gate. It's going to become important to us later on. Very large or very small numbers requires 32 bits, so 32 wires just for one number. If it is a very large or a very small number, our floating point will be this 32-bit. We will reserve the first bit for the sign. The second bit will be the exponent. Now this is the sign of the exponent, and this last part will be our fractional part. We know that in scientific notation, the standard is to have a single digit, like 1.3 or 2.456, single digit. So we are going to assume that it is a 1 out front, and then we can adjust using our exponents. And that is how we get around making really big and really small numbers. Your calculator on this would represent it as 6.023, and then if you were using a Texas Instrument, it would have a little e there, which would represent times 10 to the, and it would have just a 23 after it. Here is an example showing you how we are representing a particular value in right, in this slide, we're looking at how to represent a very large or a very small number with just ones and zeros. Notice that this bit would require 79 bits. This would require 110 bits. But we don't need something to that precision. What we are going to use is a 32-bit floating point standard. The first bit will represent the sign of our number, whether it be a positive or a negative number. The next bit will represent the exponent, and then we'll have the fractional part. Now, in standard scientific notation, we have one single digit followed by a decimal point, and then, as in these two up here, 6.023, which would mean you'd move your decimal point 23 places to the right, and you would get this very large number. This second number here, 6.626 times 10 to the negative 34, means that you would take your decimal point and move it 34 places to the left with zeros filled in between because it is a very tiny number. Let's look at this in detail. This is the sign of our number. If there's a 1 there, we know it's negative. Here's our exponent field. It is a 126 if I go and calculate that out in binary. Then my fraction part here is 0.5, still following the 2 to the negative 1, to the negative 2, to the negative 3, to the negative 4. You can see this has a lot of precision. And how this is calculated, you would do negative. We would find that this is negative 1.5 times 2 to the, and since we had this as a 126, the standard is, in solving this, you subtract off 127. If I go back a slide, it does show that you subtract off the 127 in the procedure. We're not going to actually find it, but this is the procedure in how to go using floating point, and then this number would be negative 0.75. Special values, if the exponent field is all ones, that's infinity. It means it's really big, and you can either have a positive infinity or a negative infinity. If the exponent field is all zeros, then it is so tiny as n to effect be a 0. Hexadecimal. Hexadecimal is how we're going to represent our numbers so that we can actually read them. This is because looking at all of those ones and zeros is really hard. If I were to look at this 0011, 0011 is a 3. So if I wrote down a 3 and knew that every time it just represents 4 bits, I could go, oh, that would be so much easier for my eyes to look at. And then a D, so 0011 is 1101. And if I go to D, it's 1101. Oh, that's so much easier to look at. And so you can follow through. All right, so let's see a slide that I created here. Starting from the right, just group all of your bits. We need groups of 4. And it needs to be in groups of 4 so that I can read hex. This doesn't mean anything to the computer. We're not going to do any computation or addition. It's just an easy way for us to write this because it kind of drives you crazy looking at all of these ones and zeros. So here's a few examples for us, and it just makes it easy for us to look at. 1101. I go over here and I went ahead and underlined in groups of 4 so that we could, it was already done. So 1101, I go 1101, oh, that's a D. So what I'm going to do is go, let's write that as a D so I don't have to, you mess up a 1 or a 0 and you just, computer won't know what you're asking it to do. So 1001, oh, that's a 9. So there, I could just say that's 9. This is all zeros. Now that's a 0. 1010, go to 10, oh, that's an A. Okay. Then 0101, that's 5. 1000, that's 8. Boom. That's so much prettier, and then I didn't have to write all those ones and zeros. All right, 1111, that's an F. All right, that 1011, 0, oh, that is a B. 1100, 100, that is my C. 0010, oh, that's a 2, I already know that. Ooh, 1110, that's an E. And then 0100, oh, I think I already know that's 4. All right, this is for you to do. So group these in groups of 4, hit pause, and make sure that you can group this up and get this answer. So this is a quiz question for you. Hopefully you pause that. What I get is B2415F. Hopefully you got that. If not, let me know. All right, here's an ASCII table. This is how we are going to have some text show up and what the computer thinks is. So the computer, if I write a lowercase a, all this text is in 8 bits. So if I write an A, the computer sees it as whatever a 6 is, binary, which I think it's 0110, and then 1, so that 4 bits would be 0001. And then I didn't have to write all those ones and zeros. Hex is just an easy way for us to look at it. So let's say we are going to translate the following ASCII codes. This is an ASCII code into strings of characters. So I'm going to first look at the 48. The X means that it's hex, so be sure and put the X in front whenever you write this so that someone knows that you're talking about it being hex. So 48. So I go to the hex where it says 48. Oh, that's capital H. My computer knows that 0100100 as an H. 6F. 6F. Computer says that isn't. Where's my F? 6F. That's an O. And then 77. Computer looks at that as. Where's my 77? Oh, W. 64. Computer says D. 79. Computer says Y. Then 21. In hex, 21 in hex. Oh, that's an exclamation point. All right. What you need to do for this is push pause and translate this into a string of characters. Look at your 4C and then say 4C is, there it is, it's capital L. So you will need to get out your quiz and write down a capital L and finish the rest of this string with how you're translating it, or how the computer is translating it. All right, question 4. What I need for you to do here is go backwards. So I need you to, my name is, you're supposed to take and write your name as a string of characters. So what I want you to do is put an X down because this is going to be in hex. And my name is, be sure you write down what you're using. I'll use Becky. That is my name, so I'll do lowercase x. And then I'm going to find a capital B. And I'll write down 42. And then I would want an E, so I would write down 65. And I want a C, so I'd write down a 63. And so forth. Of course, you do it for your name. So this is question 14. Question 15. Hexadecimal numbers are used for our convenience. They don't mean anything really to anybody else. They're just so that we don't have to write down all the string of ones and zeros. But if somebody said add them, what you have to do is you have to know it's in binary, and these will be in 2's complement. In this particular case, it will be in 2's complement 16-bit binary numbers. You have to know what it's in, and then you translate it. So what I will do is I will say that my 0 is 000, 2 is 001, 0010. There's 8 bits. There's my 5 is 0101. There's my 5. B is 1011. And then I did the same thing to the D there. Then I added. And then if I'm supposed to put my answer, there's the answer in binary. If I'm supposed to put the answer in hex, I group it and I get it in groups of 4. And I would say there's my 2, 1001, that's a 9. And then 0011, that's a 3, 1001. And so there's what I would get for my example. So you do this one, hit pause, and that will be your last quiz question and the end of your chapter 1 and 2 coursework. For this one, I get, hopefully you already finished it, D19C. Hopefully you can get the same thing because you will have a test question just like this on your exam. All right? See you next time.